The first time I heard the term Monte Carlo sampling, I thought it was going to be something fancy, like something they'd use in casinos to predict roulette wheels or cheat slot machines. And to be fair, the name does come from gambling. But once I actually learned what Monte Carlo sampling is, it felt surprisingly down to earth. Not mysterious, not magical. It's not even particularly complicated. Just math saying, look, the world is messy and we can't predict everything perfectly. So let's try a lot of possibilities and average them. The crazy thing is that the simple idea is powerful enough to make photorealistic rendering possible. It's how cycles simulates light. It's also used in physics, finance, machine learning, and even modern game engines. So today, I want to walk you through what Monte Carlo sampling really is, why it works, and why, despite looking incredibly simple, it's one of the most important ideas in modern computation. You're probably watching this video on Deayan Studios, but it's been released on my new channel Deayan Decoded as well, because this technique sits right in the overlap between math and rendering. It's the reason light looks like light in Blender, and also is a strategy used across some of the deepest scientific fields we have. Let's start with a problem Monte Carlo tries to solve. If you've ever rendered anything in cycles, even something as simple as a glass cup, you've probably noticed that light does a million chaotic things. It bounces off the floor, it refracts through the glass, it splits into wavelengths, it hits a wall, bounces again, slips under a table, and somehow still ends up inside the cup you placed on the other side of the room. If you try to write the perfect mathematical description of all these paths, it looks beautiful on paper, but completely impossible in practice. The actual equation, called the rendering equation, is this massive integral over every direction light could come from and every possible path light could take. There is no closed form solution. You can't just compute it and be done. So, what do we do when the perfect solution is impossible? This is the moment Monte Carlo steps in and says, we can't solve it exactly, but we can estimate it by sampling. Here's a simple way to think about it. Imagine you want to know the average height of everyone in your country. You could try to measure every single person. That's the perfect solution. Or you could go outside, randomly measure a few hundred people, and average their heights. That average won't be perfect, but it will be close. And if your random picks are truly random and you take enough of them, your average becomes extremely accurate. This is Monte Carlo. The universe quietly guarantees that randomness plus enough trials eventually leads to the truth. So, whether we're sampling light paths in Blender, or neutron collisions in a nuclear reactor, or even millions of market futures in finance, it's the same idea. Use randomness to explore the possibilities, then average what you find. Let's peek under the hood. The Monte Carlo estimator looks like this. And it really does look like basic average. And in a sense, it is. But here's the key idea. Monte Carlo isn't averaging everything. It's averaging just a handful of random samples from an impossibly large set of possibilities. And somehow that small random slice is still enough to approximate the truth. The downside is noise. In rendering, that noise is literally the grainy pattern you see when you first hit render. Monte Carlo gives you truth, but only after enough samples. The relationship is predictable. It's proportional to 1 over the square root of the number of samples. If you want to half the noise, you need 4 times the samples. If you want the noise to reduce by a factor of 10, you need 100 times more samples. So yes, Monte Carlo can be slow, but it's brilliantly reliable. It works on problems where traditional methods collapse instantly. Now we get to one of the most counterintuitive parts. Why would random sampling solve problems that exact math can't? The answer is that randomness lets us explore enormous spaces without having to check every possibility. Imagine trying to enumerate every path light could take through a room. You'd probably die of old age before you finished listing them. But if you randomly explore just a tiny percentage of those paths and average their contributions, you get something remarkably close to reality. However, not all randomness is equal, and this is where the smartness comes in. You could sample completely uniformly, or just throw rays in random directions with no guidance. Cycles would still converge eventually, but it would be extremely slow to remove the noise. So instead, we use better distributions. If a bright lamp dominates the scene, sample more rays towards the lamp. If a surface is glossy, sample more rays near the mirror's direction. If an HDRI has a bright sunspot, focus more samples there. These aren't different algorithms, they're all still Monte Carlo. They just use smarter random distributions that guide samples towards meaningful regions. This is why sampling can be done using various techniques like importance sampling, MIS, or next event estimation. However, they're not alternatives to Monte Carlo, they're enhancements inside the Monte Carlo family. If you want to make cycles faster, you could determine a smarter sampling technique and watch render times plummet as fewer samples would be needed to remove the noise. But remember, the randomness stays. The convergence just gets a lot faster with smarter sampling techniques. Now let's talk about exactly how Cycles uses this. Every single pixel in your render is an estimate of how much light reaches the camera. Cycles doesn't know the answer. It doesn't know the important parts. It doesn't know which rays matter. So for every pixel, Cycle sends out random rays. Some bounce 5 times, some bounce once. Some gets lost inside a glossy surface, and some finds a light source immediately. Each ray is one random sample of a huge complex integral. Cycles keeps track of all the results and averages them. And that's why your render starts as speckled noise and slowly turns into a clean image. You're literally watching Monte Carlo estimation converge to the truth. In this video, we explored the BSDF algorithm, which determines how light travels based on the surface. Check it out if you haven't already. But without the Monte Carlo sampling, the BSDF simply would be unable to generate realistic results no matter how many samples are calculated. What I love about Monte Carlo is that once you understand it in rendering, you start noticing it everywhere. In physics, it's used to simulate particle transport and radiation interactions. In finance, analysts simulate thousands of possible futures to estimate risk. In machine learning, especially reinforcement learning, Monte Carlo methods estimate expected rewards by simulating future trajectories. Even real-time games use Monte Carlo-inspired techniques to fake global illumination on the fly. It's one idea, but it keeps showing up in places where the world is too messy to compute exactly. There's something almost philosophical about Monte Carlo. It doesn't pretend it knows the answer. It acknowledges uncertainty. It works with randomness instead of fighting it. It's the opposite of deterministic algorithms, the ones that give you clean, exact answers. Monte Carlo embraces the chaos and still manages to find clarity. And that quiet humility combined with astonishing power is what makes it so elegant. When I first learned Monte Carlo sampling, I thought it was just a hack, a trick to get around complicated math. But the more I used it, the more I realized it's not a hack at all. It's what lets us compute the otherwise impossible computations. We can't compute the world perfectly, but we can sample it and average our way towards understanding it. It's how cycles turns math into image. It's how scientists simulate the unmeasurable. It's how algorithms navigate spaces too large to fully explore. And that blend of simplicity and power is what makes Monte Carlo one of the most beautiful ideas in computation. If you enjoyed this kind of deep dives into the ideas behind rendering, check out Deayan Studios' Demystifying series. And if you want to understand more algorithms like this, come join me on Deayan Decoded, where we break down a lot more of these profound concepts in an intuitive manner. And until those videos come out, thank you so much for watching. And as always, don't forget to stay curious.